So welcome back to the third lecture in this series. By now, if you're joining us, you've probably already heard sort of about all of Eric Maskin's extraordinary accolades, and you've certainly in the first two lectures experienced his fantastic teaching. So let me tell you just a couple of other sort of important facts about our extraordinary guest. First of all, not only is he himself a Nobel laureate, but he has trained already three Nobelists in economics, and I like to estimate sort of a large number in the future to come as well. I mean, it's really extraordinary to have sort of three of your students that win the prize in such a short time period. He is also one of the only scholars I am aware of to have his own Investopedia page. There's an official definition of Eric S. Maskin in the context of investing facts because of his tremendous impact on practical thinking around markets and market clearing. At Harvard, he has not only taught on sort of game theory and micro and auctions and such, but also a course on truth. He's a philosopher in addition to a mathematician and economist and other forms of scholar. And one more sort of fact, as if he hadn't done it all with that list, he's also a virtuoso clarinet player. So on top of all of these things, of course, and sort of foremost in our minds, especially in this session, Eric is an extraordinary economic theorist and expert in all manner of game theory, mechanism design, and today, auction theory. So thank you once more, Eric. Let's all welcome him. And then, sort of one quick piece of logistics. We're going to take all the questions at the end, except for clarifying questions, which we'd love to have in the chat. So let's welcome Eric, get some emotes in the chat, and part three, auction.
Great, great, Eric, yeah.
Well, thanks so much, Scott, for that extraordinary introduction. You're a master at that. There were some very good questions that came at the end of lecture 2, which I have not had a chance to answer yet. If there's time at the end of lecture 3, I will answer them then. But if not, what I'll plan to do is to write written answers, and they will be posted on the website. So never fear, your good questions will be answered. So today I want to talk about auctions. You're probably all familiar with auctions as a way of selling goods and services. For literally thousands of years, they've been used for selling unusual items such as art and antiques, but these days you can buy almost anything through auctions on online sites such as eBay. Auctions are used to power Google and Facebook. They sell their ads through auctions. There's been a series of very large-scale auctions in which governments have transferred large parts of the radio spectrum to telecom companies, which has made possible the telecommunications revolution. So auctions are everywhere. Auctions can be thought of as a game between the seller and potential buyers. And because of that, it behooves us to take game theory and apply it to auctions to understand what is going on. And I hope to convince you by the end of this lecture that game theory can be a powerful tool for helping us to understand auctions. So what is an auction? It's a selling procedure with rules. It's a formalized selling procedure in which the seller starts with the goods, and then there's some potential buyers who take actions. These are often making bids Perhaps the seller herself is an active participant in the auction. That sometimes happens. And then based on the actions taken in the auction, there's some reassignment of goods. Perhaps some of the buyers get goods, others don't, and there's and there's some payments normally from the buyers to the seller. I'm going to look at a special kind of auction, but a very familiar auction in which the seller is just selling one good. So there's a single item. It could be a painting. It could be a valuable security. There's this one item, and there's a number of buyers who are potentially interested in acquiring that item. And we'll describe buyer I's valuation, theta I, as the most that buyer I would be willing to pay for the item. So different buyers can assign different valuations to the item. Buyer I's valuation is the number theta I. So if the buyer gets the good and ends up paying an amount P, buyer I's net payoff is her value for the good, theta I, minus the amount that she pays. That's what's left over. And we're going to assume that the various valuations are distributed according to some joint probability distribution. For convenience, I'm going to assume that these numbers are normalized between 0 and 1. That's just to make things simpler. Now, here is an important assumption. We're going to suppose that each buyer knows her own valuation, and she also knows the probability distribution from which the other valuations are drawn, but she doesn't know other buyers' valuations. This, I think, accurately reflects the position of most buyers in an auction. They know what they're willing to pay, but they're not sure what others are willing to pay. So we're going to describe an auction as a triple for each buyer. So for each buyer, a buyer is going to have a strategy space. That's the set of strategies that buyer I can undertake. There's going to be a function HI, which depends on the strategies that all the buyers take. And that should be thought of as the probability that buyer I wins the auction if buyers take strategies S1 through Sn. So we're allowing here for the possibility that there might be some randomness in who wins. And perhaps the seller flips a coin. If the two highest buyers, if buyers are making bids and the two highest bids are tied, then maybe the seller will flip a coin to determine who wins. And then finally, we'll have this function PI for buyer I, which is just the amount that buyer I pays given the strategies S1 through Sn. And notice that this is very general. So we're allowing for all sorts of potential selling procedures, even selling procedures where buyers might have to pay something even if they don't win. So given this setup, a buyer I's payoff is her value for the good, theta I, times the probability that she wins the good, hi, minus the amount that she pays, pi. Now, from a game theory point of view, you can think of an auction in which nature moves first. Remember, in the first lecture, I said that any uncertainty in an auction can be described as a move by nature. So let's imagine that nature moves first, and nature chooses the valuations, the types, according to a joint probability distribution, mu. Now, the players don't perfectly learn what nature has done. They learn their own valuation, but they don't learn the other valuations. So in terms of the game tree, let's suppose that, that there are two players, and each player could either have the valuation theta I or theta I prime. This is what the game tree looks like from player one's point of view. There are four possible choices by nature: theta 1, theta 2, theta 1, theta 2 prime, theta 1 prime, theta 2, theta 1 prime, theta 2 prime. Notice that we have linked these two nodes for player one together in the same information sets because player one can't tell whether player two has theta 2 or theta 2 prime as a valuation. So they are linked together in the same information set, and the same thing down here. So player one knows his own valuation. He can distinguish between theta 1 and theta 1 prime, but not between other players' valuations. But one takeaway from all this is that a player's strategy will depend on his own valuation, which he knows. So how do we describe Nash equilibrium in a setup like this? The term that's often used in a setting where players are not fully informed about other players is Bayesian Nash equilibrium. It's really just a Nash equilibrium, but with some expectations. So what is this expression here? Hi times theta I. That's the probability of winning times buyer I's valuation if he does win minus his payment. But notice that we're taking an expectation with respect to theta minus I, which buyer I doesn't know. So this is the left-hand side of this inequality is the conditional expectation of buyer I's payoff if players are following their Nash equilibrium strategies, where those strategies will depend on their own valuations. So the left-hand side of the inequality is buyer I's Nash equilibrium or Bayesian Nash equilibrium expected payoff. If buyer I deviates and plays some other strategy, SI prime, that's the right-hand side. And as usual, in Nash equilibrium, it should not pay any buyer, any player to deviate unilaterally. So this inequality has to hold for all SI prime, for all strategies that buyer I could deviate to. And since this is the crucial definition that I'm going to be using for the rest of the lecture, let me just pause and make sure that, that there aren't any questions about this. Everything look all right?
Yeah, I think we're okay.
Okay. Feel free to ask about this later if you're getting confused. All right, so I said that I want to use auction theory to illuminate our understanding of auctions. Let me talk about 4 specific kinds of auctions. And I think quite a few of these you will already have seen and know about. The first kind of auction is what's commonly called the high bid auction, in which each buyer makes a bid, and these should be thought of as sealed bids. So you make a bid, but you don't know what the other buyers are bidding. And then the seller takes all of the bids, opens them up, and the high bidder wins, and the winner pays his bid. Very common sort of auction used for many purposes. Then there's an interesting sort of auction which was famously used to sell flowers, particularly tulips, in Holland. And so it's often called the Dutch auction. Quite different from the high bid auction. In the Dutch auction, it's the seller, the auctioneer, who sets prices. So there aren't any bids. The auctioneer starts with a very high price, a price so high that no buyer is likely to be interested. And what the auctioneer does is to gradually lower the price until one of the buyers says stop. And that buyer gets the good being sold at the price that prevailed when the buyer said stop. So that's the Dutch auction. And the third auction I want to talk about is the second price auction. It's also called the Vickrey auction, after William Vickrey, the economist who first studied this auction theoretically in detail. These days, it has been used quite widely as well. There are a number of online auctions which have used second price, the second price format. I don't think eBay does anymore, but they did for a while. And in the second price auction, well, it's very similar to the high bid auction. Each buyer makes a bid and the highest bidder wins. But now, instead of paying his own bid, he pays the second highest bid. And as we'll see, the fact that he pays the second highest bid gives the second price auction some very nice theoretical properties, which we will be coming to. And then the final auction I want to talk about, maybe the most commonly used auction of all. It's sometimes called the English auction. In this case, buyers call out bids openly. So you hear the other buyer's bids. Each successive bid has to be higher than the previous one. So the bids go higher over time, and the auction ends when no one wants to bid any higher. So the winner is the last buyer to have bid. No one wants to top that bidder's bid. So the winner is the last buyer to bid, and the winner pays the bid that he made. So I've now described 4 auctions in words. I want to now look at these auctions from the standpoint of game theory. So to do that, we have to say what the strategy spaces are, and we have to say what the H function is, the probability of winning is, and we have to say what the payment function is. So let's look at the high bid auction first. In a high bid auction, you make a bid. Well, a bid is just a non-negative number. So your strategy space in the high bid auction is just the positive real numbers. And what is your probability of winning given the other buyer's bids? Well, in the high bid auction, the high bidder wins. So if your bid is higher than everybody else's, you win with probability 1. However, if there is a tie among, say, M bidders for the highest bid, the normal way of resolving that tie is for the seller to randomize, where each high bidder gets a 1/m chance of winning. If you don't have the highest bid, your probability of winning is 0. So this is the HI function for the high bid auction. And what is your payment? Well, in the high bid auction, you pay something only if you win. So if you win the auction, you pay your bid, which is SI. Otherwise, you pay nothing. So we've now described the high bid auction formally with these 3 items, SI, HI, and PI. Let's do the same thing for the Dutch auction. Well, in the Dutch auction, remember the auctioneer is setting the price, and we start with a very high price, and the auctioneer lowers that price until someone says stop. But that means that the strategy space for a buyer is just the price, or a strategy for buyer I is just a point where he will say stop. So again, it's just the non-negative numbers. If you're willing to say stop when the price reaches $10.50, then your strategy is $10.50. What about your probability of winning? Well, if your stopping point is higher than any of the other buyers, you're going to say stop first, because remember, prices are coming down. So you will win if your stopping point is higher than the other buyer's stopping point. If you tie with other buyers for the highest stopping point, then again, the seller will randomize. If your stopping point is lower than someone else's, then you have a 0 probability of winning. And then finally, notice that you end up paying your stopping price if you win. You say stop at $10.50, you pay $10.50. But the interesting thing that we can see from this slide is that the high bid auction and the Dutch auction, from a game theoretic point of view, are exactly the same. Strategically, they are equivalents. And so we already have a benefits from looking at our auctions from a game theoretic point of view. The rules of the high bid auction and the Dutch auction are very different. They look quite unrelated, but as soon as you write down what auctions, you see, and we see on this one slide, that the high bid auction and the Dutch auction are really just the same thing from a strategic point of view. They are equivalent. So that's not a very deep conclusion, but it is an important conclusion. And we're going to go on to see that there are some other important and actually deeper conclusions that we can draw about these four auctions. Let me again pause to make sure that everyone is with me. Any questions about this slide in particular?
One person asks, isn't there additional information revealed during the Dutch auction and I guess possibly also the sort of applied the English auction because you're learning the upper bounds on other players' valuations?
Well, okay, so let me get to the English auction in a minute. But in the Dutch auction, yes, indeed, you are learning as the price falls that the other buyers have not said stop yet. So you are learning something about their valuation, but it's not information that is useful to you, because if you decided to stop at $10.50, you knew from the very beginning that that would only matter if other buyers didn't say stop sooner. So yes, you are learning that they didn't say stop sooner, but you already knew that your bid wouldn't matter unless they didn't say stop sooner. And so you haven't learned anything that would cause you to change your strategy.
Awesome.
That's a very good question, though. I'm glad someone asked that.
Yeah. And then one other question from Ning Liu asks, are the high bid and Dutch auctions different in terms of the domain? Like, does the sort of starting bid point truncate the domain in a way that's like meaningful for the design?
Okay, so that's an interesting point too. Here, I'm not putting any upper bounds on players' strategies. They could bid arbitrarily high numbers. Of course, in practice, people have only a finite amount of money, so this is not literally R plus. Similarly, in the Dutch auction, the auctioneer is not going to start with an infinite price. The auctioneer is going to start with a very high but still finite price. And so yes, that's a good question. The auctioneer in the Dutch auction has to make sure that the original price is high enough so that no buyer is ever going to want to bid that high. But as long as the auctioneer does that, and remember, we have limited all of the valuations to the unit interval 0, 1. As long as the auctioneer takes care to set a high enough price, in effect, the domains of these auctions are the same.
Awesome.
Very good. Let me go on. I've got two more auctions to describe. And the next thing I want to do is to show you that that although the second price and English auctions are not strategically equivalent, there is still an interesting and important sense in which they're equivalent at a deeper level. So let's first describe the second price auction in game theoretic terms. Remember, in the second price auction, you can make any bid you like. That's a non-negative number. You will win if you are the highest bidder, or you will win with some probability if you tie for being the highest bidder. Now, here's a difference with what we've seen for the other two auctions. If you win, if you make the highest bid, you don't pay that bid, you pay the maximum of the other bids. In other words, you pay the second highest bid. If you win, if you lose, if you don't get the good, you pay nothing. So that's what SI, HI, and PI look like for the second price auction. Now, one reason why the second price auction has been examined a lot in the theoretical literature and actually has been used a fair amount in practice is that there is a very simple strategy that buyers can use to bid optimally in the second price auction, which is for a buyer simply to bid his valuation. If I'm willing to pay at most theta I for the good being sold, I should bid theta I. It's a dominant strategy for me to do that. When I say it's a dominant strategy, I mean, no matter how other buyers behave, I'm at least as well off bidding theta I as I am anything else. And furthermore, there will be some cases where I'm strictly better off bidding theta I rather than something else. So here's a game where both players have dominant strategies, which are D for player one, D for player two. So D is a dominant strategy because if player one doesn't use D, well, in this case, if the other player plays C, it doesn't matter whether player one uses D or C, but notice that if the other player plays D, player one is strictly better off playing D than C. So D is a dominant strategy for player one, and by symmetry, D is a dominant strategy for two. So I want to show that in the second price auction, it is a dominant strategy for you to bid your evaluation. Now, how do I do that? Well, there are a couple of cases to look at. First, let's suppose that buyer I's valuation turns out to be bigger than the max of the other buyer's bids. And let's imagine that buyer I is considering bidding SI prime, which is also bigger than the other buyer's bids. Well, in this case, it actually won't matter whether buyer I bids theta I or SI prime, because in either case, he's making the highest bid. And in either case, he's paying the maximum of the other bids. So here it doesn't matter whether you bid theta I or SI prime, your payoff is the same either way. However, suppose that you're considering playing SI prime equal to the maximum of the other buyer's bids. Well, for SI prime, you tie with the other buyers. If you tie with the other buyers, then you don't have a probability one of winning anymore. Your probability of winning is reduced. But you get a positive payoff if you win, because your valuation is higher than the other buyer's bids. You get a positive payoff if you win, so you don't want to have the probability of winning reduced below 1. That means that you are strictly worse off bidding SI prime than you are bidding your true valuation. And that's even more true if you contemplated bidding SI prime less than the maximum of the other buyer's bids. With SI prime, you would lose altogether. You would have 0 probability of winning, which would be too bad because you have a nice positive payoff from winning. Here again, you are strictly better off bidding your true valuation rather than this lower valuation. Now, I could go through the arguments for the case where you have a valuation which is less than the maximum of the other buyer's bids, but actually that's completely symmetric with the cases that I've already gone through. So I think I will not belabor the point and simply declare that I have shown that bidding your actual valuation is a dominant strategy. You gain by bidding your valuation. So you never gain by bidding some other strategy. You never gain relative to bidding your true valuation. And sometimes you lose by bidding something else. So you want to stick with your dominant strategy. Okay, so now we've described the second price auction and how you should bid in the second price auction. What about in the English auction? Remember, the English auction has people calling out bids openly, and bids go higher and higher until until no one wants to go higher. Now, actually, in the English auction, it's really impossible to write down the strategy spaces. They are very complicated because there's an infinity of possible sequences of bids, and in principle, your next bid could depend in an intricate way on the bids that have come before. So we can't possibly write down all of the strategies. So I'm going to look at a simplified version of the English auction, which is sometimes used. And in the simplified version, instead of the buyers themselves calling out the prices, once again, it's the auctioneer who does this. So the auctioneer starts with a very low price, say a price of 0, and then gradually raises the price. And now what buyers have the opportunity of doing is to drop out. That is, as the price goes up, you say, well, I'm still willing to pay that price. I'm still willing to pay that price. But at some point, the price will get so high that you will drop out. And when you drop out, the other players can see that you've dropped out. And then the auction is over when all but one buyer has dropped out. And the buyer who has not dropped out is the winner, and he pays the price that prevailed when the second to last buyer dropped out. So this is a slightly simpler version of the English auction than the full-blown version where buyers are making bids. But as I hope you can see, it's actually very similar in spirit to the more complicated version. So we'll stick with this modified English auction. Now, it still has very complicated strategy spaces because when you drop out, when you decide to drop out might depend in a very complicated way on when other buyers have dropped out. That's an allowable strategy, but still, it's very easy to show that there's a dominant strategy for players, which is very simple in the English auction. What you should do if you're in this English auction is to stay in the auction until the price reaches your valuation, and then you should drop out. That's the dominant strategy. If you dropped out before the price reached your valuation, well, you would be getting a payoff of 0, but if you had stayed in, there would be some chance that the other buyers would drop out before the price reaches theta I. And if you had stayed in, then you would have won. And you would have had a positive payoff, because if they're dropping out before the price reaches your valuation, you're getting something that's worth theta I, and you're paying less than theta I. So you're always better waiting until the price reaches theta I than dropping out before. Now, would you ever want to wait until the price got higher than theta I? Well, you wouldn't want to do that, because if you won with a price higher than theta I, you would be paying more than the good is worth to you. It's worth only theta I to you. You don't want to pay more than that. So you should certainly drop out when the price reaches theta I. And so we see very simply that it is a dominant strategy in the English auction to drop out precisely when the price reaches your valuation. So in both the second price auction and the English auction, there is a dominant strategy which ensures that the winner is going to be the buyer with the highest valuation. In the second price auction, that happens because buyers bid their valuations, and by the rules of the auction, the highest valuation wins. In the English auction, the buyer with the highest valuation will be the buyer who is the last bidder standing. All of the other buyers will drop out before the price reaches theta I. And so once again, the winner will be the buyer with the highest valuation. Now, what about the payment that buyers make? Well, by definition of the second price auction, the winner pays the maximum of the other buyers' bids. But the other buyers are bidding their valuations. And so in the second price auction, the winner will pay the maximum of the other buyer's valuations. In other words, the buyer will pay the second highest valuation. This is true in equilibrium, where buyers are using their dominant strategies. Now, what is the winner going to pay in the English auction? Well, remember, in the English auction, the winner pays the price that prevailed when the next to last buyer drops out. Well, but the next to last buyer is the buyer with the second highest valuation. And the buyer with the second highest valuation drops out when the price reaches the second highest valuation. So that's what the winner pays in the English auction. And notice, therefore, that the second price auction and the English auction have exactly the same equilibrium outcome, that the buyer with the highest valuation wins, and that the winner pays the second highest valuation. So once again, even though the auctions are very different in their rules, and even though in this case they are not strategically equivalent, they are equivalent in the sense that in equilibrium, when buyers are behaving optimally, the outcomes are equivalent. Okay, let me once again pause and make sure that everyone's with me. Any questions about the equivalence between the second price auction and the English auction?
So one question that's come up in the chat is pointing towards common value auctions. Xiaoli Meng asks, this seems to be based on the assumption that your evaluation is predetermined. What if the evaluation depends on seeing how many bidders are still in the process?
Very, very good. So let me go back to my setup here. Here it is. This is buyer I's payoff. Buyer I's payoff depends only on buyer I's valuation. It does not depend on other buyers' valuations. And that is an important simplifying assumption. In economics, we often call this the private values assumption to contrast it with common values. There are some settings where your valuation might depend on information that other players have. If, for example, we are bidding on an oil well, you may know something about how much oil is in that well, which would be relevant to me if I knew it. So that's a case where my payoff might depend on more than just my own valuation. And that's a very interesting possibility, but it takes us beyond the scope of this lecture. Right? This is an introduction to auctions where we're assuming private values to make things nice and simple.
And if you have time for one more, Ofer Kimchi asks, why are second price auctions not used more frequently? What are the benefits, for example, of the English auction in contrast?
That's an excellent question. Actually, that's more than a clarifying question, but it's so interesting that I want to answer it now. Well, in fact, as I was saying, the second price auction is now being used a lot more frequently. For many years, it was more a theoretical construct than a practical auction, but many online auctions are second price auctions these days. You might ask, why would we ever use the English auction, which seems to be more complicated, certainly has more complicated strategy spaces than the Vickrey auction, and there are two reasons. One reason is that although the strategy spaces in the English auction are more complicated, the equilibrium behavior is extremely simple, because at any point in time, as the price is going up, all you have to do is to decide, am I going to stay in or drop out? In other words, buyers don't even actually have to figure out what their valuations are in advance. All they have to know is their valuation high enough so that it's worth staying in? So in that sense, the English auction is actually simpler than the second price auction, where you have to, before the auction even begins, you have to figure out exactly what your evaluation is. But perhaps a more important reason why an auctioneer might want to use the English auction rather than the second price auction comes back to what we were talking about a moment ago. Let's imagine that that my valuation depends on information that you as another buyer have. So theta I is not sufficient to determine how much I'm willing to bid. You may know something about the oil well that I don't know. Well, in the English auction, some of what you know about the oil well will come out in the bidding. If I see you dropping out, that will tell me you don't think there's much oil. If I see you staying in, that will tell me that I think that you think that there's a lot of oil. And that may influence when I drop out. In other words, when we drop the assumption we're making in this lecture, which is that there are private values and that buyers don't care about other buyers' valuations, the English auction and the second price auction are no longer equivalents. And in fact, you can show that the English auction is better for the seller than the second price auction. That's a rather complicated answer, but the question was so interesting and important that I wanted to get to it now. Okay, so now we have seen two equivalences. An equivalence between the high bid auction and the Dutch auction, and a somewhat more subtle equivalence between the second price auction and the English auction. I want to show you that there's an even deeper sense in which all four auctions are equivalents. Now, actually, as it stands, that equivalence is not true. I'm going to have to make some additional assumptions. The first assumption I'm going to make is simply that the density of the distribution of each theta I is positive. That's not a very strong assumption, but a much more important assumption is that now I'm going to assume that that buyers' valuations are independently distributed, independently in a statistical sense, which means that if I know my valuation, that tells me nothing about your valuation. Doesn't change my view about how your valuation is distributed. That is a strong assumption, and we're going to need it for what's coming. All right, so remember, we can describe an auction as a triple of objects for each buyer, SI, HI, PI. Let's fix an auction and let's look at an equilibrium of that auction, a Bayesian Nash equilibrium, which is going to be an n-tuple of functions. Remember, each buyer's strategy in the auction will depend on her valuation. So these strategies are functions of valuations. Now, from independence, we no longer have to look at conditional expectations, because from buyer I's point of view, the distribution of theta minus I, the other buyer's valuations, will not depend on theta I. So buyer I's equilibrium strategy will maximize this expression here. Buyer I's valuation, if she wins, times the probability that she wins, minus the payment she makes. Now, another way of looking at this maximization, where buyer I varies her strategy, another way of thinking about it is instead of varying your strategy, let's imagine varying the valuation that you pretend to have. So your true valuation is theta I, but you could always act as though you had a valuation of theta I hat. And so just as you could consider varying your strategy over all possible strategies, you could consider varying your apparent valuation over all possible valuations theta I hat. Now, of course, in equilibrium, you're going to want to choose to behave as though your valuation really is theta I, because that's your true valuation. So the maximum will occur where theta I hat equals theta I. And that's equivalent to solving this maximization. Now this expression star is what's sometimes called the revelation principle. We've started with some sort of auction, and we've looked at an equilibrium of that auction. But another way that we can think about the auction and the equilibrium is that there's a simpler auction going on, in which instead of playing the strategy SI or SI prime, you are simply announcing a valuation, which is then plugged in to the strategy SI star of theta I hat to get the equilibrium outcome of the auction that we started with. In other words, for any auction and for any equilibrium of that auction, we can think of a simpler auction in which buyers are just announcing valuations, and the outcome of that simpler auction is equivalent to the equilibrium outcome of the auction that we began with. Furthermore, in the equilibrium of this simpler auction, the direct revelation auction, buyers will be announcing their true types, their true valuations. I can announce any theta I hat I want, but in Bayesian Nash equilibrium, I am going to announce theta I hat equal to my true valuation, theta I. Once again, this is an important point. I'm going to be making use of this in what follows. So I should make sure that everyone is with me. Any questions about this slide?
I think we're actually okay. We've been responding to a couple of comments about the information structure and so forth.
Okay.
But I think we're okay.
Okay, good. All right, so now I'm going to simplify notation a little bit. So this expression here is buyer I's expected probability of winning if he pretends to have a valuation of theta I hat, and all of the other buyers are using their equilibrium strategies. And notice that because we're expecting out the other buyers' valuations, this expression depends only on theta I hat. So I'm going to use the simplified notation, gi of theta I hat, to denote I's expected probability of winning if everybody else is behaving according to their equilibrium strategies, and buyer I is acting as though his valuation is theta I hat. Same thing with buyer I's expected payment. Ri of theta I hat will be buyer I's expected payments if he bids as though his valuation is theta I hat. And we're once again expecting out the other buyers' valuations and strategies. So let's go back to this condition here, which just says that when choosing which theta I hat to play, I should, in equilibrium, I should choose theta I hat equal to theta I. Well, that just says that when you're maximizing this expression, your valuation times your probability of winning minus your payments, you should choose theta I hat equal to your true valuation. And this should be true regardless of what your true valuation is, regardless of what theta I is. So let's assume that the expression in square brackets here is differentiable. Actually, you can prove that except at a finite number of kinks, it will be differentiable. But let's just assume that it's differentiable. Then we can look at the first order condition for this maximization. The first order condition is right down here. This is an identity in theta I. The maximum occurs where theta I hat equals theta I. So this first order condition is an identity in theta I, which means that we can reintegrate it to obtain this connection between gi and ri. As you all know, when you integrate, there'll always be a constant of integration, and that is a boundary condition, which we'll call Ri of 0. And now we've established a very interesting result called the revenue equivalence theorem, which says that suppose that we have two auctions. The rules of these two auctions might be completely different. And let's fix a Bayesian Nash equilibrium in each auction. And suppose that the G functions are the same in those two equilibria. Remember, GI is just the expected probability of winning in this auction, and GI naught is the expected probability of winning in this auction. Suppose that the G functions are the same, and suppose that the boundary conditions are the same. So Ri of 0 is how much a buyer with a zero valuation can expect to pay in the auction. Obviously, RI of zero is never going to be positive, because if you have a zero valuation, you get nothing out of winning. So you're never going to want to pay a positive amount. But RI of zero could be negative. You could imagine an auction where even if you don't win, you get something. Let's look at two auctions where the G functions are the same and the boundary conditions, the RI of zero, is the same. Well, then it must be the case that the amount that you pay in expectation is the same for all valuations theta I. And this is called revenue equivalence, because from the seller's point of view, the RI is how much revenue the seller gets from buyer I. So we're saying that we have two auctions where the expected probability is the same, the amount that a zero valuation a buyer pays is the same, then every buyer and every possible valuation for that buyer will be paying the same expected amount in both auctions. That's actually a pretty powerful result, because it means that in order to understand what's going on in an auction, we just have to figure out what the G function is and what the boundary condition is. And then everything else that we care about, how much the buyers are going to be paying, how much revenue the seller is going to get, will be determined from those two things, the G function and the boundary condition. And I want to apply the revenue equivalence theorem to our four auctions we've been talking about. To do that, I want to make one more assumption. I want to assume that the underlying distribution of the valuations is the same for each buyer. So I've already assumed that the theta i's are drawn independently. On top of that, I want to assume that the theta i's are all drawn from the same distribution. So this is what is called an IID assumption, independent and identically distributed. So the theta i's are drawn in this IID way. Okay, what I'm going to show you is that all four auctions are equivalent from a payment point of view, a revenue point of view. Let's begin by looking at the second price and English auctions. We already know that they're equivalent in terms of equilibrium outcome. So in equilibrium, in the second price auction, a buyer bids theta I. In the English auction, buyer drops out at theta I, and that means that the buyer with the highest valuation wins. So what is the GI function for the English auction or the second price auction? It's just the probability. If your valuation is theta I, your probability of winning is just the probability that every other buyer has a lower valuation. Well, the other buyers' valuations are being drawn from the same distribution, F. F is the CDF of the distribution. The other buyers' valuations are being drawn independently. So the probability that all the other valuations are less than theta I is just F of theta I raised to the n-1 power since there are n-1 other valuations. Any questions about this equation?
One question is, where do we use the independence assumption?
Right here. This formula depends on independence.
Yeah, and I think that's it for questions.
It
Everyone
would
else
be-
seems to be tracking.
Oh, okay. So we've nailed down what the GI function is in the English auction and the second price auction. We also know by the rules of those auctions that if you're a participant and you have a zero valuation, you're not going to pay anything. So we know what the boundary condition is. And now we can conclude that Ri of theta in the English auction and the second price auction are the same. Let's move on to the high bid auction. And if I talk about the high bid auction, I'm also talking about the Dutch auction because they are strategically equivalents. Right. So studying the high bid auction is a little bit more complicated because unlike the English auction and the second price auction, there are no dominant strategies in the high bid auction. In other words, how you bid is going to depend on how other buyers bid. That's not, that makes life more complicated. Now, it can be shown, remember in the first lecture we showed, we proved Nash's theorem, which says that an equilibrium always exists. We could have used the same methods to show that in a symmetric game, a game where all the buyers look the same going in, there must be a symmetric equilibrium. It's a simple extension of the argument I gave in the first lecture. So let's look at a symmetric equilibrium of the high bid auction. Remember, buyers may end up having different valuations. However, before nature has chosen those valuations, all buyers are symmetric because their theta i's are being drawn from the same distribution. This is where we're using the identical distribution part of the assumption. So that means that all buyers will have the same G function because they're all using the same strategy. And they'll have the same R function. Now, suppose that we can show that a buyer's bid in the high bid auction is strictly increasing in her valuation. Suppose we can show that, and I will show you that in a minute. If S of theta I is strictly increasing in theta I, then the highest valuation buyer will win because this bid will be highest for the highest valuation. So if I can show that S of theta I is strictly increasing, we're going to get exactly the same G function that we did for the second price auction and the English auction. And that means, and of course, in the high bid auction, you pay nothing if you have a zero valuation. So we're done in showing the four-way equivalence of our auctions as far as payments and revenue go, if we can show that S of theta I is strictly increasing. Okay, so we're going to do this in two steps. First, we're going to show that the G function in the high bid auction must be non-decreasing. It can never go down. And to see that, let's fix two possible valuations, theta I naught and a higher valuation, theta I double naught. Now this inequality is an equilibrium condition. If my valuation is theta I naught in equilibrium, I am better off acting as though my valuation is theta I naught than acting as though my valuation is something else, theta I double naught. So this is an equilibrium condition if my valuation is theta I naught. But there'll also be an equilibrium condition if my valuation is theta I double naught. That's this inequality. Same thing with the roles of theta I naught and double naught reversed. Now I can multiply the second inequality by -1, and then I have to change the direction of the inequality, add them together, and I'll get this inequality here. That's just a little bit of algebraic manipulation. Now we know that theta I double naught is bigger than theta I naught. So this expression is positive. That tells us that this expression is non-negative. So that tells us that the probability of winning in the high bid auction has to be non-decreasing in your valuation. It's pretty intuitive that it should be non-decreasing. If my valuation goes up, I should be willing to bid more, but this is a formal proof of that intuition. But we have to go a step farther and show that GI is not only non-decreasing, but strictly increasing. And in particular, that the bid is strictly increasing in theta I. So that's this next claim. So we know that the bid function has to be weakly increasing. It can't be it can't be decreasing anywhere. Well, suppose that it's not actually strictly increasing. Suppose that there's an interval where S is flat. The bid function is flat on the interval from theta naught to theta double naught. That means that at the lower end of this interval, a buyer makes the same bid, B star, as at the upper end. This is something went wrong with my slide. Ignore that. Now, if your evaluation is in this interval, you'll be bidding B star, but that means that you're going to tie for having the highest bid with positive probability, because anybody whose valuation lies in this interval is going to be bidding B star. And this interval occurs with positive probability. This is where the non-zero density assumption is being used. So you're going to tie with positive probability. However, let's imagine that you bid very, very slightly higher than B star. that's going to very slightly reduce your payoff if you win. However, now you don't have to worry about tying with any of the buyers whose valuations lie in this interval. And so your probability of winning increases discontinuously. So your probability of winning increases discontinuously. Your payment, if you win, increases just a tiny bit in a continuous fashion. And so you are better off bidding B star plus epsilon than you are bidding B star. That tells us that we cannot have flat portions of the bid function cannot be constant on an interval. We cannot have flat portions of the bidding function. And so we have proved that in the high bid auction as well, this is the revenue equivalence theorem again, your G function is just the probability that everybody else has a lower valuation, f to the n minus 1. And so we have shown that all 4 auctions have the same revenue function, payment function, even though those auctions have very different rules. And here's an interesting point. We know that in the second price auction or in the English auction, you don't pay your bid. You pay the second highest bid. And so from that point of view, the seller is getting less than she would in a high bid auction where buyers are actually paying their bid. So the high bidder pays that bid. But notice that in the high bid auction, buyers are never going to want to bid their valuations, because if they did bid their valuations, they would get nothing. They would be getting, if they won, they would be getting something worth their valuation, but they'd be paying their valuation. So their net benefit would be 0. So in the high bid auction, buyers will always bid less than their valuations. And what we've shown here is that those two effects are exactly offsetting, so that it turns out that revenue in the second price auction is exactly equal to revenue in the high bid auction, at least under the assumptions that we're making here, including the fact that the theta i's are drawn independently and identically. Well, I think that's a good place to stop. And as I said at the outset, I think auction theory is a good illustration of how powerful game theory can be in contributing to our understanding. Auctions are important. We will all agree on that. And I've taken you through a number of arguments. None of those arguments were very complicated or difficult. I could do it all in a single lecture, but the results are very powerful. We've learned a lot about these 4 auctions and the connections between them just on the basis of some simple analysis. So I hope one lesson that you take away from this series of lectures is that a little auction theory can go a long way. And let me stop there and see what questions might remain. And feel free to ask questions about previous lectures at this point.
Eric, that was totally awesome. I mean, this whole series has really been a tour de force in showing how, mathematical framings and formulations let us make really powerful statements in economic theory, in ways that you can like do on slides, right? Like totally amazing. Let's thank Eric and get some applause in the chat. And then, goodness, we have lots of questions, which assuredly we don't have time to do all of, but let's maybe do a couple. And then Eric, you said you might be able to like take some of them offline in some form.
Yes, as long as Sergey preserves the chat, I will get to. I will try to get to many of these questions offline, and they will be posted on the center website.
Amazing.
Really great lectures, Eric.
Thank you.
So maybe just a couple while we still have a few minutes today. So one of the recent questions is the revenue equivalence theorem is really interesting. What are the boundaries of this result? Is there a similar question when the valuations are not IID, maybe like also getting into common values and so forth?
Yes. So the revenue equivalence theorem does use every assumption that I invoked. Symmetry, the fact that the valuations are being drawn independently, the fact that they are being drawn identically, and the fact that we are ruling out common values. For all of those, if any of those assumptions is dropped, it is no longer true. If there had been more time, I would have shown you what happens when we drop the symmetry assumption, the identical distribution assumption. Second price auctions and English auctions behave very well, even when there's asymmetry across buyers. In other words, in the second price auction, it will always be the case, even with asymmetry, that the buyer with the highest valuation wins, because buyers are always bidding their valuation. But interestingly, in the high bid auction, if we introduce asymmetry across buyers, that is, their valuations are being drawn from different distributions, it may no longer be the case anymore that the winner has the highest valuation. I'm not going to go through the argument because there's not enough time here, but imagine that there were two buyers. The buyer one's valuation is drawn uniformly on 0.1, buyer two's is uniformly on 0.2. It will turn out that that buyer one may outbid buyer two, even if buyer two has a higher valuation. It sounds strange, but it can easily happen. And similarly, that of course breaks revenue equivalence, because revenue equivalence depends on having the same G function. But the high bid auction here clearly has a different G function than in the second price auction.
Excellent. And that incidentally is a really good, highlight as well, right? That like, as the math also lets us sort of like disentangle like which assumptions are necessary, and like how as you change the information or the valuation environment or whatever, the results and our understanding of which auctions to use moves around.
That's right.
Excellent. So I think we're at time. Yeah, I don't know if you want to say anything to close the series.
Well, let me just repeat what I said at the outset, which is that I was interested in giving these lectures because I think it's a good thing for mathematicians to know game theory. Game theory was originally created by mathematicians, in particular von Neumann and Nash, And eventually it got taken over by us economists and also biologists, et cetera. But that isn't to say that mathematicians can't come back and still make useful contributions to game theory. I hope I've persuaded you that that the game theory questions are interesting. And if any of you would like some guidance about reading, please feel free to contact me about that.
Awesome. Yeah, no, and indeed a lot of the biggest innovations in game theory and market design and all of these fields these days have been through collaborations between economists and mathematicians, or sort of through people who are both an economist and a mathematician, such as yourself.
I should also say, for those of you who might be interested in computer science, there's enormous computer science and game theory these days. And Harvard is a good illustration of the collaboration between computer scientists and other sorts of game theorists.
100%. All right. So I think that will wrap us up. Let's thank Eric one more time, and thank you, Yao, for hosting the series, and Sergey for helping chair and answer questions and so forth, and then Elena for juggling and organizing. Thank you all, and QED.
Well, thanks. I think it's really great to listen to Eric, and I think you gave a great lecture. I really enjoyed it. Thank you.
It was my pleasure.